All right, so now we're moving into chapter 8. Chapter 8 is somewhat of an extension of some of the things that we were talking about with regard to solutions and reactions that occur in solutions. So we're going to see in chapter 8 a lot of aqueous solution stuff, which means primarily speaking, we're talking a lot about single replacement and double replacement reactions and how those reactions, we can kind of get a little deeper into them. So we need to start with just kind of a simple review of what a solution is and kind of what makes up a solution. So by definition, solutions are homogeneous mixtures. And they are comprised of a solvent, which is basically the substance that is present in the most amount. Ordinarily, especially in this chapter, we're going to focus on water. Water being the solvent in almost all of these cases, where water is dissolving various ionic and covalent compounds along the way. And then solute, basically whatever is dissolved in that solution. So those are the two generic components of any solution. We've got the solute and the solvent. The solvent does the dissolving. The solute is usually the substance that we're interested in terms of chemical reaction. When a substance is dissolved in water, we refer to it as an aqueous solution. Aqueous solutions are solutions where we have water as the solvent. And if you think back to chapter 7, again, we talked about those phases of matter that you can put on balanced chemical equations. We show aqueous solutions as AQ in those kinds of chemical reactions. And again, primarily, we are dealing with single replacement and double replacement reactions when we're looking at aqueous solution chemical equations. Now, here's something we have not talked about yet, but you've probably heard these terms thrown around. When it comes to aqueous solutions, we can describe them in two different ways. We can describe them as electrolyte solutions, or we can describe them as non-electrolyte solutions. Which category they go into depends on what's dissolved in them and what happens when those substances get dissolved. So for electrolyte solutions, what we will see are the presence of ions in the solution. And as a result of the ions being present in those solutions, they will conduct electricity. And on the other hand, we'll have non-electrolytes. Non-electrolytes are solutions that do not conduct electricity. And that is because in those solutions, we'll either have no ions present or we'll have very few ions present in those solutions. So whether something is an electrolyte or a non-electrolyte has everything to do with ions. If the substance has ions in it, or if it, when dissolving, breaks apart into ions, then we will find that that solution conducts electricity. If it doesn't break down into ions, or maybe it breaks down into just, very, very, very few, we'll find that it doesn't conduct electricity at all. So we're going to focus our attention now on electrolytes. Electrolytes are substances that will conduct electricity when they are dissolved in water. And this conductance is going to come from one of three categories of substance. We're either going to have ionic compounds, salts, which, because of our discussion of nomenclature, we should have a pretty good idea of what those look like. Usually they are metallic and non-metallic elements or ions brought together. We should also be able to identify acids. That is substances whose chemical formulas start with H. So if it has hydrogen and then something else, chances are pretty good that it's an acid. And then we have bases. Bases are substances whose chemical formulas tend to end with OH. So we can very easily pick out by chemical formula whether a substance would be electrolyte or non-electrolyte just by looking at it. Now, those are common ways of identifying acids and bases by chemical formula. Now, as it turns out, there are other ways of doing so. And it gets into what we call Bronsted-Lowry theory. That Bronsted-Lowry theory of acid-base allows us to identify acids and bases based on their behavior, not based on their chemical formula. And so there is a slight distinction there. Under the Bronsted definitions, an acid is basically any substance that will give away a proton or an H+ ion when it comes into contact in a reaction. So if I look closely at this chemical reaction, I can see that if I compare the HCl and the chloride ion, to go from HCl to chloride, it had to have lost an H+ ion. Under the Bronsted definition, that would make HCl an acid. Now, based on our own kind of inspection identification, we already knew that HCl was an acid in that scenario anyway. But now we can see that in the reaction, it is also behaving the way that we would expect it. By contrast, if I look at the water has gone from H2O to H3O+. In the process, it has gained an H+ ion. Under that definition, given to us by the Bronsted-Lowry theory, that means that water in this particular case is acting as a base. Now, under our identification, water doesn't end in hydroxide. So we wouldn't have predicted that water is basic. And under most circumstances, it isn't. If I take the pH of pure water, I'm not going to get a base. But what this definition does is it identifies acid-base reactions as occurring based upon the movement of that H+ ion. And what it says is that when acids act like acids, there's always a base that they have to interact with to give them that acidic behavior. They're not naturally acidic on their own just because they happen to have hydrogen in them. They have to react in some kind of way. If it's an acid, it's going to take that H plus that it has and it's going to give it away. If it's basic, it's going to take in an H plus, even if it has hydrogen already on it. What this does is it takes that relatively narrow view that we had of acid base as, okay, acids have hydrogens, bases have hydroxides, and we can now open it up a little bit and identify acids and bases based upon reactivity, not just chemical formula. And so that's what this is all about, helping us to identify acids and bases based on reactivity, not just, oh, it's NaOH. Of course it's a base. Oh yeah, it is a base. It's a base because when it goes into the water, it takes the hydrogen away from water and deposits another hydroxide. Strong acids. There are 6 strong acids that you need to be aware of. Good chance that you're already aware of most of them. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric. And the only one that you probably haven't seen too much of is this last one, perchloric acid. These are the acids that you need to familiarize yourself with. Because if the acid is on this list, it's a strong acid. It behaves in a very specific way. That specific way is that all of these ionize. And so as a result, strong acids are going to give us very electrolytic solutions. They're going to conduct electricity very, very well. If an acid is not on this list, it's not a strong acid. The only other category for it is weak acid, and weak acids behave by different rules. Weak acids are what we call weak electrolytes. They conduct electricity, but poorly. And the reason they do that is because instead of what we saw before, where everything ionizes, we get low ionization with weak acids. Strong acids, 100%. Every molecule turned into 2 ions. Lots of ions present, high conductivity. Weak acids, we get low ionization. Somewhere right around 5% or less ionization. Now, some of that depends upon the concentration as well. It can fluctuate a little bit. But if you can imagine, for every 100 molecules, only 5 of them actually break apart. That means that the other 95 stayed together. And so if you have one of these weak acids where 95% are staying molecular and only 5% are actually producing ions, you know that you're not going to get a whole lot of ions in that solution. It's going to conduct electricity, but not nearly as well. With bases, we see similar kinds of properties. Now, your strong bases are going to be your hydroxides for the first 2 columns of the periodic table. The only real exception to those is in group 2 At the very top of that group, the magnesium and the beryllium, their strength isn't quite as pronounced. They're on the weaker side. So with strong bases, once again, we see all of them will ionize. Whereas weak bases, we get partial ionization instead. So strong bases conduct electricity very, very well. Weak bases conduct electricity poorly, but they do conduct it at least a little bit. Amphiprotic substances kind of have their foot in both doors. Again, this goes back to we can't have amphiprotic nature if we don't have an understanding of the Bronsted-Lowry theory. Again, this comes back to reactivity, not identification of hydrogen or hydroxide. When we can pinpoint reactively that a substance can act both as a base and as an acid, depending upon its environment, we call that substance amphiprotic. Water is a great example of an amphiprotic substance because water can exist as an acid when we put it with stuff that's more basic, or as a base when we put it with stuff that's more acidic. And the product that forms, hydronium or hydroxide, it can go either direction. It's equally likely to form those. It just needs the proper environment. All right, let's close today looking at this practice problem, and then I'm going to get your feedback one more time before we close up shop on today. Let's identify the acid and the base in this chemical equation. Now, to do that, what we have to do is we have to track the hydrogen. So we've got two sources of hydrogen, both in the same molecule here. If I look on the other side, I can see that those hydrogens haven't moved. So it's not the hydrogens in the CH3 that we need to monitor. It's this hydrogen right here. And we can see that this hydrogen has left and been replaced by sodium. So this is a double replacement reaction. The substance that has lost hydrogen is this. This is acetic acid. So we would identify this as the acid. The substance that has gained the hydrogen specifically is the sulfur. So that would mean that the sodium sulfide is our base under the Bronsted definitions. So once again, it all comes to tracking the hydrogen. Where is the hydrogen going? To where is it going? From where did it come? That's how we can identify acids and bases.